Okay. So I have finished the previous session with this slide. Okay. So remind that I have defined the moment generating function. When it exists, it is given by this quantity here. Okay. I have done the computation for Poisson, Gamma, Gaussian. Okay. The three that you have to know. We have seen together that this moment generating function characterizes the distribution of a random variable. That is, if you have two random variables having the same moment generating function, they will have the same distribution. Okay, so to prove that two random variables have the same distribution, it's sufficient to prove that they have the same distribution function, the same moment generating function. Okay. And we have seen together that if I have two random variables that are independent, okay, the moment generating function of the sum is just the product at the same point. So it means that this little relation will be a powerful tool in order to compute what is the distribution of a sum of two independent random variables. So together we have done the job for the Poisson in the previous session. I have proved, I have recovered the fact that if I have a Poisson of parameter lambda 1, a Poisson of parameter lambda 2, if they are independent, the sum is a Poisson of parameter lambda 1 plus lambda 2. Everybody has received my email concerning the midterm. I have sent it to you. Yeah? Yeah. Be careful, huh? I have written this in my email. The program is not the same because we have 1 month, okay, more or less between the midterm in the previous year and this year midterm. Okay. But I think that I will also send you the final exam because at the beginning of the final exam you have exercise that will help you in order to have a look on the midterm. Okay. If I have time today, I will start it today, the beginning of the final exam of the previous year. Okay. So let's continue with this idea here. Okay? I have to do some other cases. So the first one, that is in fact an exercise of the list 6, that is the exercise 3. And the idea to do this one is to use the moment generating function. And I will say a few words at the end concerning another way to do. And it's a good training to try to do at home with the other methodology and to see that at the end, okay, the computation are not really the same. 2 pages in one case, okay, and 2 lines in one other, okay? So, but the statement is very simple and it's a result you have to know. If I have x1 that follows the n m1 sigma 1 square, if I have x2 that follows a Gaussian with mean m2 invariant sigma 2. If I suppose them to be independent, okay, I want the distribution of x1 plus x2, okay? It's 9, huh, always, huh? We don't change the rule because it's only based tomorrow, huh? Okay. So, what we will use is this result. Okay? The fact that I can compute, in the case of independence, the moment generating function of a sum this way. And I just have to remind what is the moment generating function of a Gaussian random variable. So to remind something we have seen during the previous session. Do you remind or not? No? If you don't know, okay, the aim is to know it in 3 weeks, okay? So it's exponential t M1 plus sigma 1 square T square over 2. You agree? That don't seem to be surprised. It's something I have computed during the previous session. Huh? And for the other Gaussian, I have the same. Okay? So in order to find what is the distribution of the sum, one possibility, and here it will be particularly well adapted to my situation, because here, if you have a look on this result, you have the moment generating function of the sum that is given by this product, and when you do the product of exponential, it's perfect for you. Okay, because the product of exponential is the exponential of the sum of what I have inside the exponential, so it will be very easy to simplify the things. So if I want the distribution of the sum, okay, I just have to compute. One way is to compute the moment generating function of the sum. According to the proposition I have reminded on the board, and that is the proposition 21, part 2 of my slides, then the moment generating function of the sum is equal to what? To the product of the moment generating function. Okay? So you have here m x1t, m x2t. I have just to replace and see what happens. Okay? So I replace by what I know concerning the moment generating function of x1 and the moment generating function of x2. And of course I can regroup some terms, okay? And I can write the things this way. Okay? I have this. What can I conclude? So now I have computed the moment generating function of the sum. I know that the moment generating function characterizes the distribution of a random variable. Okay, so if it is possible to recognize the classical moment generating function, my job is finished. It's exactly what I have here. What is this? Well, it's the moment generating function of a what? It's a Gaussian. M1 plus M2, sigma 1 square plus sigma. Okay? So I recover here, in fact, very basically, with few lines, the fact that the sum of two independent Gaussian random variables is still a Gaussian random variable with a mean that is the sum of the mean and the variances that is the sum of the variances. So if you have some time during the holidays, you can try to do the following one here. To see the fact that the moment generating function is a really powerful tool. Okay? So in a few minutes we are going to do the exercise 2 of the list 6, okay? Where we are going to use this one. For the moment I have used it, maybe one, I don't remind if I have given an example, maybe yes. Excuse me. This one, the proposition 16, okay? That is how to obtain the density function of the transformed pair, okay? So an application of this proposition 16, that will be exactly what we are going to do in the exercise 2 of the list 5 and the list 6 in a few minutes, okay? But should be to do the following. So I start with a pair that is x1, x2, okay? I am exactly in the setting of this proposition because they are independent. I know the density of each component, so I know what is the joint density of this one. The joint density is the product of the density of each component by independence. Okay, so I start from my x1, x2 as in the statement of the proposition 16. And the idea is to have some news about this one. As you see in this exercise, be careful, you change a pair into a pair. Okay? So it means that if I am interested in this one, okay, that is the transform of this one, I need to find or to deal with another one in order to start from 2 and to go to 2 random variables. So I can do the following. So I will transform basically this vector by putting inside what I want. Okay, I want some news about x1 plus x2. And I want to complete the things in order to obtain a vector of size 2, but I can put x2. So at home, you can try to apply to this transform here. So you have here, okay, with my notation, g1 of x1, x2, that is equal to x1 plus x2. You have g2 of x1, x2, that is equal to x2. You can try to apply this, okay, in order to obtain the joint density of the pair, okay, by proposition 16. And at the end, if you want the density function of this one, what you have to do, if you know the joint density of this one, just compute the integral with respect to the second variable of the joint density function. Okay? But try to do at home, and you will see, with respect to this solution, the number of computation that you will do in order to do this. And you will see that there is a big difference. Okay? That is okay. In the chapter 8 here, I have to learn what is a moment generating function and what are the basic moment generating functions. But once I know this, okay, then I have the flexibility to do computations that are very short. Okay? So it's a good exercise. Okay? That is a little bit in the spirit of the homework I have given to you to do at home. Okay? You will see, I tell you directly, the computation in the homework are horrible. Okay? But that's why I ask you as an homework. Because you have time at home, okay, you are, okay? Horrible, it's a big word, okay, but not that easy, let's say, okay? It's in the spirit of this one. So try to exercise, because if you are able to do them, okay, for the simpler that I can ask you during an exam, okay, you will be totally okay to do them, okay? So try to do this at home, okay? And maybe if you want, so I won't do this during the Zoom session for sure. Huh? I don't want to spend half an hour doing computation on my computer on my little board in my home, okay? So we can discuss about this one, okay, after the holidays. But I won't solve this one by this technique, okay, during the Zoom session for sure, okay? Because I need to do too much computations. Okay, exercise 6 and 3 of list 6. So let's continue with this idea, okay? We are going to do 1 or 2 more examples of this type, okay? And typically, you will see in finance that when we work with Gaussian, in fact, we use, okay, in very few situations, the density function of Gaussian, we use moment generating functions because they are more flexible to handle. Okay. So I keep this one because I will use it again, and maybe you can try to do by yourself. Well, before to do the exercise 5, okay, I will do this one. So it's an example following, okay, this proposition. Okay, the sum of gamma. Okay. So I consider the statement, the exercise or example. I consider x1 that follows the gamma, let's say A lambda. Okay. I have an x2 that follows the gamma B lambda. Okay. They are independent. And I ask you, what is the distribution of x1 plus x2? And try to do it by yourself, this. Okay. Okay, so I have two, yeah? I have two independent gamma. You see that here, they have the same lambda. Okay? And of course, if you have understood, the idea will be to use the moment generating function. But you will see that in a few minutes, I will do this job, okay, in another way, using the proposition 16 before. And you will see that the computation are not exactly the same. So you have everything on your notes because I have already done the computation of the moment generating function in the case of a gamma. Okay? You are looking for the moment generating function of the gamma? So after the definition, for sure, you have it here. Just after the definition, I have done some computations. Poisson, gamma, n01. So if you have understood, 1 minute to do. You can consult your notes, okay, in order to have the moment generating function of a gamma if you don't know it for the moment. Okay. Of course, that to be correct with the definition of a gamma, I need to impose A strictly positive, B strictly positive, and lambda strictly positive. For sure. Okay. That seems to be. Yeah. So just be careful. Okay. Little remark, but T, you have some condition on T in order to be able to write this. Okay. Excuse me? Yeah. Okay, so
what to do if you say x1 minus x2 multiply in this case minus
this one?
yes,
Yeah, this one is the same than this one.
yeah, it can be plus minus x2.
You will obtain you will obtain nothing, okay, in this case, because minus a gamma is not a gamma. Okay, but if you want to compute what is the moment generating function, it's possible to do. Okay? You are interested in this kind of quantity. Okay? Okay? If you have this, don't have a look on this, okay? Try to do this one, I just answer a question, okay? So you have this one, you can use independence. You obtain the moment generating function of x1 at the point t multiplied by the moment generating function of x2 at the point minus x. You replace and you see that you can't do anything. So it's not a noun distribution, this one. Okay? No, you don't have the same lambda and alpha. They have the alpha that are different and the lambda. Yeah. Okay? Lambda are the same, not necessarily alpha. It's mandatory to have lambda that are the same if you want to do it. be able to say something. Okay. It's okay? So if it's okay for the one that are okay with this one, you can do, because it is exactly in the same spirit, okay, after this one you can do the exercise 5 of the list 6. Okay? If you have already finished with this one, try to do the exercise 5 of the list 6. If you don't have the exercise 5 of the list 6, okay, I can give it to you here. It's very short statement in relation with the chi-square distribution. And at the end, you just have to say that here I recognize the moment generating function of a gamma a plus b lambda, so x1 plus x2. Okay. Is it okay for the gamma? For everybody? Okay, that I have used this expression here in order to be able to compute the derivative part here, but a priori, to come back to what you have done, okay, it's better with this one. I say it's easier to know this one. Hmm?
We should use the logarithm one, right? We should use the one for logarithm, right?
No, wait, this one, the one I have computed and the one you have, that you will have to know after the holidays. I have already done the job. I have done the computation of the moment generating function of gamma distribution. So of course we are going to use this. Huh? Now it's in the course, so you can use it if you know. It's okay for everybody for the gamma? So what is mx1 of t? In my example, okay, it's the one of gamma, okay? So it's lambda over lambda minus t to the power a, okay? And I need to impose a condition, okay, on t in order to make this quantity okay. I need that lambda minus t is strictly greater than 0, okay? So t is strictly less than lambda. I have the same for the other random variable because they have the same distribution, okay? Just the parameters are changing. It's lambda over lambda minus t to the power b, okay? It's lambda lambda minus t, that is also strictly positive. And now I just use this one, I multiply, and I see that I will recognize something I know. So by independence, I have this one. Okay, by independence, I have this one. I just replace, and I obtain what? I obtain lambda over lambda minus t to the power a, lambda over lambda minus t to the power b, or lambda minus t is greater than 0. And I can simplify, okay, because I have the same quantity inside. That's why I need the same lambda. If you don't have the same lambda, finish. You can do. Okay, so if you don't have the same lambda, you have the moment generating function of the sum. But the only problem is that you don't recognize something you know. Okay, in this situation, it's not the case because I can write it this way. Okay, and what I can say here is that here I have the moment generating function of the gamma a plus b lambda. Okay. So really, it's longer for me to write the statement than to do. The only computation I do is this one here. For the other thing, okay, I just use the proposition and so on. Okay, but I have nothing to compute. It is what is nice with this kind of tool, okay, is that the computation are really basic, okay, for most of distributions. I recognize the moment generating function of a gamma a plus b lambda. So this one, okay, is just a little box. Okay? You will see that. So there is a, if I come back on the list of exercise here, there is a misprint in the list 6 here. Exercise 2. So I have to do something that we are going to do after, okay, but in the exercise 2, here you have to change between the parameters. It's gamma A1, gamma B1. If you try to do this way, okay, you can try to do, it's like if here I invert the parameters. If I invert the parameters, I can say anything, okay? So I will say it again, but here and here in the exercise 2, there is a misprint where you have to invert the two parameters here, okay? It's because I have taken this exercise from a book, and in the book they use different convention for the notation of a gamma, okay? I have used alpha as the first parameter, lambda as the second one, lambda being the one on the exponential. We do the converse, okay? And in fact, what we are going to recover from this exercise and this part here is exactly what I have done, but we will do it using proposition 16. Okay, and you will see that it will be more complex to do this job here than to do this little computation here. But whatever, so I will come back on this exercise after. Exercise 5. So are you okay with what I have written here? I don't think that it is too much complicated, so, but you have to know things. You have to know the moment generating function of gamma, and you have to know this, okay? And then to use at the end that the moment generating function characterizes the distribution. So if I recover a known moment generating function, it implies that my random variable follows my known distribution. Okay, exercise 5 of the list 6. This one. So it's something that I have started to do. So in the exercise 5 of the list 5, we have defined what is the chi-square distribution with n degrees of freedom. Okay? It is gamma n over 2 1/2. And here I want another characterization of this distribution, that is to be, in fact, something that I have already said in the previous session. It's the sum of the square of any independent n01. I want to prove that a gamma, so a key-square of parameter n, that is a gamma n over 2 1/2, is none other than the density of the sum of the square here. Okay? So try to do. It's not complicated. It's not complicated if you know what is the moment generating function of a gamma, but you have it here. If you know what is a key-square of parameter n, that is a gamma n over 2 1/2, and then you can do the job. Okay? Yeah. So today I will let you work a little, okay, to change the real beginning of my holidays, in fact. I don't have to work. Perfect. It will. Okay. The other one. Let's go to this before. So, I am looking with you that I am not a big believer. Yeah, square. The square of a Gaussian is not a key-square of parameter n over 2 over 2. What is the n here for single one? Yeah, we know what it is. So just a remark concerning the methodology, because it's the way I will do it. You can do this directly, okay, using interwine lines, not a problem. But my remark is the following. What happens if I don't have IDs? I don't know, okay? So keep in mind that you have a property to prove for any n, okay? So what may be an ID in order to do this? Yeah? Okay, so in fact, in this particular case, to do induction or not, okay, is more or less the same thing, okay? Because the induction is very basic and not that more complicated or less complicated than to do the direct things, but It's just a reminder concerning the fact that when you have something to prove for all n belonging to a subset of the integers, maybe instead of doing nothing, you can start an induction. Okay? It's one way, one possible. So if you have already finished, okay, I give you the list of what I will do, okay? Maybe the one, yeah. And if you have already finished of this one, okay, you can have a look on the midterm exam I have sent it to you. And if you have already finished this one, the final that I will send just now. Okay, I will send you there. So I just put it. Okay, so correction of the exercise 5 of the list 6. So this one. I can do it by induction, so it's not the only way to do. You can do also a direct reasoning that works, okay, no problem. But it will be the way to remind an induction. So what I have to prove is that for all n belongings to n star, if I write in a slightly different way the statement, x1 square plus n tilde xn square follows a chi-square of parameter n. Okay, a chi-square of parameter n if x1, xn are, so here I use n independent and 0. Okay, so it means that once I will do this result, the way to consider a chi-square of parameter n should be just to consider the sum of the square of n independent Gaussian n01. Okay? It will be equivalent. Okay, so let's do it by induction. For n equal to 1, okay, I am interested in x1 square. Okay? We have already done the job together concerning this. In the exercise 5 of the list 5, we have seen together that if I have the square of a Gaussian, it's in fact chi-square of parameter 1, okay, or gamma 1 half 1 half. Okay?
Yeah.
In general, okay, in the midterm or in the final exam, if I want you to put something, I will tell you to prove. If I don't ask explicitly, it means that I consider that things are in the course and that you can use them. Okay? Because typically, suppose that I ask you this kind of question in the midterm. Okay, so if you do the induction, you will see that it will take you 3 minutes to do the induction, but if you want to recover this result, in details, it is a little bit long, in fact. So you have two possibilities: to take the distribution function of this one and have a look on the density, okay, and then to recognize that the density you obtain is the one of a gamma 1 half 1 half. Okay, for a question that would be, I don't know, 2 or 3 points, okay, you don't have to spend an hour for sure. So what we have done in class, okay, what we have done during the tutorial, if you want to use the result, you can. If I want you to explicitly prove something, I will ask you to do. Okay? If it's not, you can use without any proof. Okay? And typically in 1 hour, you won't have the time to prove a lot of things. Okay? So don't spend too much time in one question, because one question will be for sure few points, okay? So I have this. So I have initialized my induction. Now we are going to suppose that it's true for n, and see what happened for n plus 1. Okay, so my induction hypothesis is just that x1 square plus until xn square follows a chi-square of parameter n. Okay, it's my induction hypothesis. And I know that a chi-square of parameter n is just gamma n over 2, 1/2. Okay? So now I am interested in what? I am interested in what happened for n plus 1. Okay, so it's the heredity step of the induction. Suppose that it works for n. Let's see that it works for n plus 1. Okay, well, let's do. So I am interested in x1 square plus xn plus 1 square. And as usual, when you do an induction, the idea is to see how I can use my induction hypothesis. Okay, so how can I use the fact that the square of the sum of the n first is a chi-square of parameter n. So how to make appear what I know here? You have x1 square plus x2 square plus until xn plus 1 square, and here you have some knowledge about x1 square plus x2 square plus xn square. So what can I do with my sum here? I can split in two parts. I will make appear what I know. That is this one. Okay? So I can write it this way. x1 square plus x2 square plus until xn square plus xn plus 1 square. Okay? Just in order to make appear something in relation with my induction hypothesis. Okay? So from my induction hypothesis, I know that this one follows a chi-square of parameter n. Okay? By the induction hypothesis. I know what is the distribution of this one. It's what? It's the square of n01. So it's typically a chi-square of parameter 1. Okay? So here I have a gamma n over 2 1/2. And here I have a gamma 1/2 1/2. What is more, what can I say about these two random variables? This one and this one. They are independent. Okay? These random variables are independent because x1, x2, xn, xn plus 1 are independent. Okay, so I have independence here. And in fact, this exercise, that's why I have done it this way. It's not more complicated than this one, it's exactly this one, in fact. Okay, but just I have to write the way to do the reasoning, and once I have done this, okay, but at the end, it's exactly the same kind of exercise as this one. Okay, so are you okay with what I have written? Okay? So I erase this part. So now, what I will do, but we are going to use, so in fact, what I have two random variables that are independent, that follow a gamma, and that are independent. If I know the result of this one, okay, it's finished. If I don't remind, I can do the one-line computation. That is to see that the moment generating function of x1 square plus xn plus 1 square at the point t, so by independence may be written as moment generating function of x1 square plus until xn square at the point t multiplied by the moment generating function of xn plus 1 square at the point t. Here I use independence here. And then I use the fact that I know the distribution of each of them. Okay? I know the distribution of each of them. Here, x1 square plus xn square by induction hypothesis follow a chi-square of parameter n. Okay? So what is the moment generating function? Something like this. 1 over 1 minus 2t to the power n over 2. Okay? Of course, I need to have a hypothesis on this one, okay? And I will write it just after. And here you have a chi-square of parameter 1, that is a gamma of 1 half, that is just 1 over 1 minus 2t to the power 1 half. And this is true for 1 minus 2t, that is truly positive. Okay? And now it's finished because I can simplify a little, okay? Because what I have here and here are the same, so I can write that I obtain, okay, 1 over 1 minus 2t to the power n plus 1 over 2, or 1 minus 2t pretty positive, and here I recognize the moment generating function of a chi-square of parameter n plus 1, and it's finished. Okay. And I have done the job by induction. Okay? So from now on, okay, an equivalent way to have a look on the chi-square of parameter n is just to see this distribution as the distribution of the sum of the square of n independent n0, 1. Okay. So if you have understood what I have said, a little remark concerning this exercise. Suppose that I am in this, yeah?
Can I just ask, why can you say the sum is independent? Because when we have two independent variables, it doesn't mean the sum of them are independent.
So, what we have seen together is the following. I have stated for 2, but it's the same for n. I have said that if you have x and y that are independent, okay, I have also, in fact it's an equivalence, that any function of x and any function of y are independent. All of them are, okay? When I say this here, so when I say x1, xn plus 1 are independent, okay, it implies in particular that x1, xn is independent of xn plus 1, consider as a random variable, okay? And then, what is the sum of the n first square? It is just, okay, this way. So any mappings that you can build from x1, xn will be independent of any random variable you can build from xn plus 1. Always. Okay? So the idea is exactly the same as this one here. Independence is something that is preserved when you do the composition by mappings. Okay? So it's an important remark because it's something typically in the statistical part, we will always work with x1, x2, xn that are independent realization of the same random variable, and we will use a lot this kind of remark. Okay? So now I will do my remarks. So are you okay with this computation? Yeah?
That's a small question. Like, we don't know that x n plus 1 is independent from the others, like, given the questions.
Yeah, you have it.
And
You have it.
what could be the, can you be like n minus 1 till n minus 1?
When you do an induction, okay, what I prove? I initialize and I say that if I suppose it for n, I have it for n plus 1, but you can say exactly that. You initialize, you suppose for n minus 1, and you prove it for n. Okay? But keep in mind that in my induction hypothesis, I suppose that x1, x2, xn are independent. So when I want to prove the result for n plus 1, my beginning is x1, x2, xn plus 1 are independent and 0, 1. Okay? It is included. I know that they are independent because it's what I want to prove. But if you want to write an induction not passing from n to n plus 1, but n minus 1 to n, no problem. So, I repeat, are you okay with this computation here? And not that complicated, I think. Yeah? So I erase, and I do a remark. So what is the answer of the to the following question here? Suppose that you are in this situation here. You have x1 that follows the t-square of parameter n. Okay? You have x2 that follows the t-square of parameter k. I suppose that x1 and x2 are independent. Okay? And my question is, what is the distribution of x1 plus x2? So of course, it should be possible to do the computation and to obtain the result, but in relation with the exercise we have done here, if I have a look on the t-square as the sum of the square of n independent Gaussian. So first, what is the answer? Imagine that I will speak like you. Okay? Okay? So what you say? Yeah? Why? So, why? Because I can do the computation using moment generating function and prove that I have this. One possibility. But if I have in mind this interpretation here, what is this one? Here I have a sum of the square of n independent and 0, 1. Here I have the sum of the square of k independent and 0, 1. I know that x1 and xn are independent, so the random variables involved in the sums will be independent. So when I do the sum of the two, I have a sum of the square of n plus k independent and 0, 1. So that's why I have this one. Okay, it's one very basic way to have it intuitively. If you don't have it, okay, do the computation and you will see that it works. Because I know exactly what is the moment generating function of this one, I know exactly what is the moment generating function of this one, so I am able to do the job for the sum. Okay, and I recognize for the moment generating function of the sum, the moment generating function of the gamma n plus k over 2 1/2, that is exactly what I want. Okay. So I have this one. So before just to continue exercise, okay, I will spend just 5 minutes in order to finish the course, okay, concerning moment generating function. It remains to do one slide, okay? And after we will continue the exercise. Do you have some question concerning what I have done here? It's okay? So I will start after this. Okay? This one. So I have already defined, okay, and we have done computation typically today. If I have a single random variable, the moment generating function of x is just the expectation of exponential t times x when it exists. Okay? In this definition here, I introduce what is the moment generating function for, in fact, a pair, but I can extend to a triple. Okay? So suppose that you have not a single random variable x, okay, but that x is in fact a pair of random variables, x1, x2. Okay, you have a pair of random variables. In fact, I have the possibility to define the moment generating function of the pair, okay, this way. So the moment generating function of the pair, I can write it this way, x1, x2. So will be a mapping depending on two variables, okay? The moment generating function of a single is a mapping depending on t, okay? The moment generating function of a pair will depend on two variables that I will denote. Okay, I have written x1 and x2 here, but here, let's say t and s. And what is this one? In fact, this is the expectation of the exponential of t x1 plus s x2. So this is the way to define the moment generating function of a pair of random variables. Okay? Of course, this expression, okay, that's exactly what I write on. I just change the name of the variable. x1, x2 here, st in the board. Okay? So of course, as all the moment generating function, if I take the value at 0, I obtain 1. I obtain what? What is this? 1. Written on the board, but because I have 0, 0, exponential of 0, 1, expectation of 1, 1. Okay. So, my moment generating function of the pair is this one. Okay? How to recover the moment generating function of the components from the moment generating function of the pair? How to recover this one from this expression here? No. So, what is this one? This one is this one with x1 instead of x here. Okay? x1 is this one. I just want to recover this one from this one. If you compute derivatives, you will make appear x1 or x2 here, okay? Not what I want, okay? Computing the derivative is to order to justify that when I take the value of the derivative of the moment generating function at 0, I recover the moments of my random variable. Okay? That's not my question here. So, no. So, you have this expression, okay? This one, okay? And I just ask you, okay, what can you do in order to obtain this one here?
S equal to
Yeah, s equal to 0 simply, okay? If I take s equal to 0, I make this term disappear and I recover this one. Okay, so I have the moment generating function of x1 that is none other than the moment generating function of the pair taking at the point t0. Okay? The moment generating function of x2 is just the moment generating function of the pair taking at the point 0, s. So it means that when you have the moment generating function of a pair, you have inside the information concerning the moment generating function of each component. Okay? Now after the holidays, okay, the part of the course where we are going to use this one, okay, will be what I will call Gaussian vectors. Okay, so I will spend time on Gaussian vector. That is just a Gaussian random variable is a random variable with values in R. Okay, one dimension. We are going to see how it is possible to extend this definition to vectors. That is in a dimension that is higher than 1. This notion is the notion of Gaussian vector. How to define a Gaussian vector we will see after the holidays, but what would be nice is that the moment generating function of Gaussian vectors will be very easy to compute. Okay? As always with Gaussian things. Okay, so just a remark concerning the notation, because suppose that I don't have 2, but that I have n. Okay, if I have n, I can do exactly the same thing, okay? So I can define n of x1, xn. So I need to have n variables. So I will now denote it 1 by x1, x2, xn. And what is this? It will be the expectation of exponential x1, x1 plus x2, x2 plus xn, xn. So if I don't want to use this big expression, okay, but I can use the following one. So I have two vectors here, a vector with the variable and the vector with the, okay, the points where I take the moment generating function, okay? This linear combination here may be written using the notation of the scalar product. Okay? It's just the scalar product. So if I give a name, okay, where x is the vector x1, xn, and capital X, that is the vector. I remind you that when you are in R to the power n, the scalar product between two vectors is just the sum of the product of the components. Okay? So for most of you, you do optimization, so I think that you know what is the scalar product. Okay? I hope. But whatever, if you don't want to use this one, okay, use this one for the moment, but you will see that after the holidays, I will use, okay, when I will deal with vectors of random variable, I will use matricial notations instead of the one writing everything, because I want to have compact expressions for the things. For the moment and for the midterm, don't worry about this one, but I will spend more time on this, okay, when I will work more deeply with random vectors. So, the moment generating function has been defined for 1, I can define it for 2, for n, okay? For a finite number, no problem with it. Just I continue my remarks, okay? Who is this? Here, this moment generating function can also be written the following way. Because here, I have a random variable here. That is t x1 plus s x2, that is the linear combination of, okay, x1 and x2. So it means that this moment generating function may be written as the moment generating function of this random variable, t x1 plus s x2, at which point have the definition, have in mind the definition
ETS1 and multiplying with ETS2.
So, at which point?
Just leave like that, and because the numbers and we can
No. I have nothing about independence for the moment. Nothing about independence. I don't know if x1 and x2 are independent. In general, they won't be. The next remark will apply after concerning independence and this. Okay, but for the moment. So what is the point is missing here? 1. Okay. 1. Have a look on the definition of the moment generating function for a single random variable. If I replace x1 by t x1 plus s x2, so I don't write a t here, but let's write a u. Okay, I obtain what? It's the exponential of u t x1 plus s x2. Okay, and if I want to obtain this one, I have to take u equal to 1. That's why I have this. Okay. So in fact, what you see here is that the moment generating function of a pair, in fact, is related with the value at 1 of the moment generating function of any linear combination of the components of the vector. Okay. Any linear combination. Okay. So in general, to compute, it's not that easy to compute this one. We are going to see in 1 second one case where it will be very basic to compute, but in general, it's not that simple because, in fact, you have a double sum or a double integral to compute. Suppose that, so I have my definition here. Okay? Suppose that you are in the discrete case. Okay, what is the definition of this one? If I am in the discrete case, I can define m x1, x2 at the point ts as, but I have in fact the expectation of a function of a pair of random variables. Okay, so I write it as a double sum. Of what? Exponential t, let's write it this way, xj plus s, write it t xi, yj, let's write it this way, okay, time the probability that x1 is equal to xi intersected with the probability that x2 is equal to yj. This is the expectation of what I am interested in. The xi are the possible value for x1, the yj are the possible value for x2. Okay? What I am interested is computing this one, that is just a function of x1 and x2, and I can compute it knowing the distribution of the pair, and I apply the classical definition of the expectation, that is just the sum of the values of the mapping multiplied by the probability mass function. Here it's just the probability mass function of a pair, that's why I have a double sum here. Okay? If I am in the continuous case, that is in the case where the pair x1, x2 is a joint, has a joint density function, but then if I want to compute the moment generating function, it will be what? It will be a double integral. Integral minus infinity plus infinity. Integral minus infinity plus infinity. Of what? Of exponential t x1 plus s x2 multiplied by the joint density of the pair x1 x2 at the point x1 x2 d of x1 d of x2. So that's why I say that in general, okay, it's not that simple to have the moment generating function of a pair or even of an upple, because I will have to compute multiple sums or multiple integrals. Well, it's possible to do, huh? But maybe, and you will see that in what we are going to call Gaussian vectors, it will be very easy. Very easy. Okay? So, of course, there are situations where it's very easy to compute it. So what you say, in the case that I have independence, no problem concerning the computation. Why? So are you okay with this? Huh? It's just the definition of the expectation concerning, okay, pairs of random variable in the discrete or in the continuous case. Jointly continuous case, the case where I have a pair of two discrete random variables. I will finish before the break by this one. So if I am interested in this one here, okay, the definition. So I said that in general to compute it, but I need to compute double sums or double integrals, but there is one situation where, in fact, it will be that easy to obtain this. That is this one, okay, the definition. And so, if I suppose independence, what can I say? I have here something that is independent of the other, and so the expectation of the product is equal to the product of the expectations, and so I have this. And here, in fact, I can express the moment generating function of the pair in terms of the moment generating function of each component, mx1 t, mx2 s. Be careful concerning this relation here I have written involving independence. It's not this one. Here you have the moment generating function of the sum at the point t, that is the product of the moment generating function. You have the same point here, t and t. Okay? Here it's not what I have. Here I have a t in the first, a s in the second, that correspond to the two variables I have in the moment generating function of a pair. Okay? Of course, I can recover this one from this one, just taking t equal to s. Okay? And I obtain this. But in the case of independence, okay, the moment generating function of the pair, that is a mapping depending on two variables, is equal to the product of the moment generating function, the first one taking at the first variable, the second one taking at the second variable. So I have this one. And we are going to finish with the last result of this section. That is the proposition 22 that I won't prove. Well, it's not that complicated. If you ask me on Wednesday, I will do the proof. It's not that long, but I don't want to spend time on this today. But that I have the converse. If I want to prove that two random variables are independent, okay? So what I can do in general? In the discrete case, I can prove that the probability mass function of the pair is equal to the product of the probability mass function of each component, one way. In the continuous case, I can prove that the joint density is the product of the density function of each component. So another way to prove, okay? But you will have a new tool now, that is, in order to prove that two random variables are independent in the discrete or in the continuous case, you will just have to prove that the moment generating function of the pair, that is this one, is equal to this product here. Okay, so independence implies this one implies independence. Okay? And we will have a criteria in order to prove that two random variables are independent, just checking what happened for the moment generating function of the pair. Okay? And typically, and once again, in the case of Gaussian vectors, it will be very basic to prove independence. Okay? And typically, we will see that after the holidays, that if I take x1, x2, so this pair that is, let's say, a Gaussian vector, I don't have given the definition for the moment, whatever, that is the natural extension of what is a Gaussian dimension 2. And we will prove with this nice property here that if I have a Gaussian vector, the components are independent if and only if the covariance is 0. Something that is really powerful, because what you know in general is that independence implies covariance 0. I have said to you that be careful, covariance 0 in general doesn't imply the independence. Okay, it's not true in great generality, but in a particular situation it will be, because we are going to use this one, okay, in the case of Gaussian. Okay, so 10 minutes. Okay, so let's do exercises. So from the list 6, do the 1 and the 2. So start by the 1. So in this exercise, I give you a joint density. So it's important to read the statement, because here I tell you that it is a joint density. Okay? So typically, you know that if you compute the double integral, you obtain 1. It's not necessary to do the job, because I tell you that you have a joint density function. Okay? And what I want you is just to compute from the joint density the density function of x. So it's what I call marginal distribution here. It's the density function of x, the density function of y, and ask me if they are independent. Okay? I do it. In fact, it's just an exercise in computing two integrals. Okay? So a priori, to do this one, it's this one that you have to use. But if I give you a joint density, you can deduce the density of each component computing the partial integral, okay? And to check if I have independence, I just have to check if the joint density is the product of the density function of each component. Okay? So do it by yourself. Exercise 1 of list 6. So my joint density is given by just a remark before to do the computation. When you have a look on this one, okay, can you see a link with some distribution we have seen together in class? Just by the form, exponential. Okay, I have negative exponential, or gamma maybe, okay. So it won't be Gaussian because I don't have square in the exponential, okay, but I have negative exponential. So maybe I can keep in a corner of my mind that the result concerning exponential may be not too far from what I have to use. So you have this density function, this joint density function, okay? And I want the one of x, the one of y, and to check if they are independent or not. So you have everything here, huh? Okay? So don't copy what I have written, it's exactly what is written in here. good matter. Yeah? Okay. Okay. What's happening? It's negative. So write the statement, you have it here, okay, and I will just put the result you have to use, okay. The statement 2 and the statement 3. And if you have already finished this one, do the exercise 2. Then do the midterm, and then do the final, and then go. Keep in mind that when you do, so when you compute the density of X, okay, have this one, okay, so I plug inside, and be careful because indicator function are part of the density function. You don't remove them. If you remove, okay, you have a problem. Okay, they are inside. So when I replace here, I have what? So I integrate with respect to y. y has to be strictly greater than 1, so it will be an integral from 1 to plus infinity because of the indicator function involving y, and then it remains x exponential minus xy, indicator function of x strictly positive, dy. Don't forget this term here, okay? Because it is in the function, the mapping. So, what can I do? I see that I have terms that doesn't depend on y. I can remove them from the integral because it's an integral with respect to y. Okay? So I have x, indicator function of x strictly greater than 0. And then I have an integral to compute. This one. It's just the integral of an exponential to compute. Okay? So you don't need to use integration by part or anything else. Okay? You just have a classical primitive for this kind of mapping. What is the primitive of exponential minus xy? Keep in mind that I do the integration with respect to y. So x is considered here as a constant, a strictly positive constant, but a constant, okay, when I do the integration. So what is the primitive of exponential minus xy? Is when I integrate, x is like a constant here. I know what is the primitive of an exponential this way. This one. Okay? It's finished. What happened in plus infinity? So that is when y goes to plus infinity. 0 because it's a negative exponential. Keep in mind that my x here is strictly positive. So here you have a negative exponential because x is strictly positive. So the limit of this term when y goes to plus infinity is 0. 0. And what happened at 1? At 1, so if I remove this one, I have just exponential minus x divided by x. That will simplify with this one. Okay, so I have minus x. And what I recognize here, what is this density? I know it from the course. Which one? Exponential of parameter? 1. So, in this exercise is not that important, but to recognize something you have in the course. Imagine, for example, that I ask you find the variance of x. You know from the course that the variance of x is 1. Okay? You don't need to do the computation because it's something from the course. Okay? So when you deal with density, okay, the first question is, okay, maybe it's something that I have in my course or in my tutorials. If it's yes, it's nice for you because you have a lot of results involving these classical densities. Okay? So x follows an exponential of parameter 1. Why not? Okay? So here, nothing to do with probability. It's just a computation of an integral. And I repeat that if you are not okay with this kind of computation, you have the holidays to do, or to be. Okay, for the other, so the density of y is given by the integral of the joint density function with respect to x. Okay? It's the joint density function of the integral of the density function with respect to. So I plug inside, okay, so what I have? So x is strictly positive, so it will be an integral from 0 to plus infinity here. Of what? Of x exponential minus xy dx. And I don't have to forget the indicator function that y is strictly greater than 1. Okay? So here once again, so I can compute this. I can do the job by integration by part typically. Okay, I can do an integration by part. I want to compute the derivative of this one. I am able to integrate this one. I can obtain the result, but I have already done the job. It's not necessary to do. What can you say about this integral here? It is related to what? So exponential. So keep in mind that I integrate with respect to x here. Okay? So the variable of integration is this one and this one. So it means that since I have x here, okay, it's not the integral of a density function, but it's more something that is related to the expectation. Because I have the integral of x times something that looks like, or that is not very far from the density function of someone. And what I have here? I have the beginning of the density of an exponential of parameter y. Okay? But it means something to have explicitly this density, because exponential of parameter lambda is lambda exponential minus lambda x indicator function of x positive. So if I want to make the density of an exponential of parameter y, okay, what can I do? I can do this. If I do this, I have exactly what I want. Because I can express this integral just as the expectation of an exponential of parameter y. But if I do this, of course, I multiply by y, so if I do this, I have also to divide by y to be sure that I have what I want. And now, I can say, and once again, without doing computations, that here you have the expectation of an exponential of parameter y. And what is this? What is? It's 1 over y. The exponential of parameter lambda has an expectation equal to 1 over lambda. Okay? 1 over lambda. With the notation I have used in the course. Okay? And at the end, I obtain what? I obtain just 1 over y squared indicator function y strictly greater than 1. This is my density function for y. Okay? And here, a priori, it's not a known distribution. So it's something that I have already seen, but whatever. It's not an exponential, it's not a Gaussian, it's not a uniform, it's not a gamma. It's this one. So what is important here? So I repeat, of course, if you want to compute the integral in white here, you don't need to do what I have done. You can do computations. That is, okay, in order to compute the integral of this term with respect to x, okay, I can do the integration by parts, but in fact, integration by part is what I have done when I have computed the expectation of an exponential of parameter lambda. Okay? So I think that it's better for you to recognize what I have already done and apply the result, instead of doing an integration by part with possible mistakes, okay? And here I have a negative exponential, so I am sure that I'm not very far from exponential distribution. Okay? So I repeat that it's not the only way to do, but doing this, okay, I just use my course and don't compute. Something that personally I prefer to do. Okay? But I repeat, if you don't want to learn this, okay, you compute the integral of this term, doing an integration by part, and you of course obtain exactly the same result. Okay? Last question, are they independent? Yes, no? So in order to check this, okay, it's the statement 3 in the proposition 15. To be independent when I have a joint density is equivalent to the fact that my joint density can be expressed as the product of the density of each component here. But is it the case here? So you have the density of x, the density of y, and the joint density here. I know. If you do the product of this one and this one, you don't obtain this one. And typically, in fact, in order to answer this question, it's not necessary to do the computation of the density of x and the density of y, because I can see it directly here. You have a joint density. I know that it will correspond to independent components if I am able to separate. You have from one side the variable x and from the other the variable y. Here I have this term, exponential minus xy, where I won't never be able to separate in a mapping depending on x and a mapping depending on y. Okay, so directly on the density function, okay, I can say that they are not independent. Okay, I check it, okay, using my proposition 15, but here directly, it's not possible to separate this density into a part that is only depending on x and multiply by a part that is only depending on y. Not possible because I have xy in the exponential here. Okay? So no independence for sure. Okay? Once again, I repeat that here I just have to compute using a classical primitive, and here to use what I know from the course. Questions? No? Okay? Now we are going to use this one. The proposition, you are going to use the proposition 16. Okay? So I want you to apply this proposition in order to do the exercise 2 of the list 6. So I will write the statement on the board and I will keep this proposition here. So what is the exercise 2 of list 6? It's this one. So there is a mistake I have said to you in the statement. So in fact, part of the exercise was already done together using the moment generating function, but whatever. Here I want you to use the proposition 16. Exercise 2 of the list 6. So what is my situation here? I start from two independent gamma. Okay? I have. So I use the notation of my statement that are not exactly the notation of my proposition 16, but I have done the job this way in order to make loop flexible concerning the notation. Okay? So x is my first random variable, initial one that follows. So be careful here. It's not a gamma 1a, it's a gamma a1. It should be possible to obtain a lambda here, okay, but whatever. For the moment, I keep this. And I take for y a gamma b1. And in fact, my job is to transform these two random variables into a new pair defined this way. I take for S the sum, and I take for Z what? X over X plus Y. Your job is the following. Using this proposition correctly, I want you to find the joint distribution of the new pair, that is the joint distribution of SZ, and to obtain from this joint distribution the distribution of S and the distribution of Z, and at the end to check if they are independent or not. Okay, so three things. Find the joint distribution of this new pair using this one. Then once you will have the new joint distribution, find the distribution or the density of each component, computing the partial integrals as I have done in the previous exercise, and concluding to the fact that they are independent or not. Okay? So I let you time to do it by yourself, okay? And typically, okay, the use of this proposition 16 will be the main tool that you will have to use for the homework. The homework is based on the use of this one. Okay? You have seen that you have the homework on the website, huh? Okay? And I want it for the day after the holidays, November 3, something like this, it could be. And on a paper, written, or if you want to use an iPad or something like this, you can. Okay, I just want to have a file, okay, or a paper, November 2. Okay? Allez, do it by yourself. Okay, so here, what may disturb you is the fact that I don't have the same notations, okay, but it's in order to make you understand really this proposition. So my x1 and x2 here I just x and y, and my new variables that are y1 and y2 are just called s and z here. And I want you to check all the things here in order to be able to apply this proposition. Do it by yourself, and I am here if you have some questions. To do it using moment generating function. I have said to you that you need to have to use the proposition 16. So you can use it's possible to. Okay. But in fact, even if you want to do it with moment generating function, you will have to use something like this. It won't be possible to do it directly. Or you will have horrible integrals, horrible double integral to compute. Okay. I prefer you to use this proposition. You can try at home to do with the moment generating function, but here I have two random variables, I transform them, I have typically in the setting of this proposition. Yes? whiteboard? Someone has a pen for the whiteboard? No? Not that, but I don't use it. Okay, so we express the transform, okay, to express S and Z as function of X and Y. I define J1 and J2 this way, okay, and I am interested in the set of definition and the set of the possible values for G1 and G2. So X and Y are gamma, okay? What is X of omega and Y of omega in the case where I have two gamma distributions? When I follow a gamma distribution, I take values that are a little bit more strictly positive. Okay? I have X of omega that is equal to R plus star, and Y of omega that is equal to R plus star. It's important to have this in mind because at one time I will have to invert something. If I say nothing about the set of definition and the set of the possible values, I will have some problem in order to invert, for sure. So here it means that my set of definition for X and Y is R plus star times R plus star, and here the same. Because the set of the possible values for the random variable are the strictly positive real numbers. Okay, now my set of possible values. For G1, I do the sum of two strictly positive numbers. What I obtain as an image of G1 by the strictly positive numbers. Okay? So here I have R plus star. Okay? Doing the sum of two strictly positive numbers, I recover all the strictly positive numbers. What happened for this one? You do the ratio of X and X plus Y. What do you obtain as a range for the mapping G2? So 0, 1, okay, but what can you say about the bounds? They are not inside, the open interval. I agree with this. My set of possible values here is this one, because you have X plus Y that is strictly greater than X. So you are sure to obtain a number that is strictly less than 1 and strictly greater than 0 because they are both strictly greater than 0. Okay, and you obtain all the numbers between 0 and 1 doing this. Okay. Are you okay? You don't see the blue?
No, I don't see.
You don't see anything? Okay. Yeah, that's why I will write on it again. Because it's the most important part of the exercise, in fact. If you have done this, after it's just to apply the proposition. So my first transform G1 associated to any X and Y is true. And I have said that it is from R plus star times R plus star into R plus star. Okay? For G2, from R plus star times R plus star, X, Y, X over X plus 1. And here, okay, keep in mind that R plus star here and R plus star here are coming from R plus star here and R plus star here. Okay, it's the set of the possible values for capital X and capital Y. And this one, I had just said that it takes values in the open interval 0, 1. Okay? Okay, so but now I have my problem that is well posed. Okay, now I just have to check that I have the right to use this. Okay? So I have to be able to invert G1 and G2. Okay? So that is, if I consider this system here, I have to be able to express it this way. Okay? Not with me. Okay? I have to invert. So I have a system with two equations and two unknowns. So just be careful because it's not a linear system. Yes, in fact here it's a linear system in x and y, whatever. Because I multiply. So how to obtain? But for z it's not that complicated because I know that the sum is s. So I have x over s that is equal to z. So z is equal to x. Excuse me, I say stupidly. Stupid what I have written here. If I have to express s and z and here s and z, it's not that complicated to do. Okay. So what I want is x and y. It's better. So for y or for x, x is equal to z times the sum is equal to s, so x is equal to z times s. Okay? X is equal to z times s, and so what is y? Y is s minus x, so it is s minus z times s. So it is s minus z times s, so it is this one. I just invert. I solve the system, okay, in terms of x and y. Okay, so what are my h1 and h2? So h1 and h2 are this way. That associate to S and Z, and the first one associates S times Z. The second one associates S1 minus Z. Okay. I have this one. So S is in R plus star, S in 0, 1, R plus star times 0, 1. My possible values are in both cases R plus star, R plus star. So you have the inverse this way. Keep in mind that I have proved that here my S take values in R plus star and my Z take values in 0, 1. That's why I have this set of definition here. Okay. And now it's finished. I have just to check the hypothesis and to apply the formula. I want to prove that G1 and G2 have continuous partial derivative. But of course they have continuous partial derivative because I have classical mappings. Here it's a linear mapping, so no problem. And here it's a ratio for which the denominator is never equal to 0. So I have no problem. I can compute any derivative I want, okay? They will be continuous because it's classical mapping, so no problem, okay? Concerning this and this one. This one because it is a polynomial, and this one because it is a ratio where the denominator is never equal to 0 because x and y are strictly positive. So they are, okay, as I want. because of their form. So now I am interested in the matrix of the partial derivatives. So if I compute the derivative of this one with respect to x, I obtain d of j1 with respect to x, with respect to y. This one, a little bit more complicated. Okay, so with respect to x, I have to compute the derivative of a ratio, u prime v minus u v prime over v squared. It's the derivative with respect to x. U prime, that is 1, v, that gives rise to this term, minus u v prime, that is x, divided by v squared. We have this one that is just equal to y over x plus y squared. It's the derivative of j2 with respect to x. Let's compute the derivative of j2 with respect to y. U prime is 0, v minus u v prime over v squared. This one. Okay? So you have here the matrix of the partial derivative. If I compute its determinant, I obtain what? So if I am interested in the determinant of the matrix of the partial derivative, this one times this one minus this one times this one, I will have some simplification because I will have minus x over x plus y squared minus y over x plus y squared. That will give me minus 1 over x plus y. And what can I say about this quantity? I know that x and y are strictly positive, so it is never equal to 0. Never equal to 0 because x and y are strictly positive. So I have checked that this is fulfilled. I am never 0 here because x and y are strictly positive. Okay? And now I just have to apply the formula. Okay? Because I have checked all the things here. And this is the main point of the application of this kind of result. Okay? The way to prepare, okay, how to use the formula in red at the end here. Okay? So if I apply the formula directly, I keep this for the moment on the board. So I use the proposition 16. It tells me what? Okay, so with my notation. So the density function of the joint density of SZ is equal to what? It's the joint density of the pair x, y, taking at the point h1 and h2, h1 being sz, h2 being s1 minus z. So I have here sz, s1 minus z, and then I have what? I have the inverse for the absolute value, the inverse of the absolute value of this one, that is x plus y, that I have to express in terms of h1 and h2, but x plus y, we have seen that x plus y is just s. So I have here s. So this is the formula in red applied to my equation. This is the formula in red applied to my case with my h1 and h2 that are given by this one, okay, and the fact that my determinant is given by this one. So the inverse is equal to minus x plus y. The absolute value is x plus y because x and y are strictly positive, okay, and x plus y expressed in terms of s and z is just s. That's why you have s here. So a priori, what I have done here can be done without any, not without any assumption on x and y. It's just, okay, what I have used here is that x and y are strictly positive, but if you have x and y that take strictly positive value, you can write this for any type of distribution. You can write for exponential, for gamma, for p square, okay, of course, because they are the same. But, okay, this one, I just used the distribution of x and y in what I have done here, here, and here, simply. And now we are going to start to use our hypothesis, the fact that x has a particular distribution, that y has a particular distribution, and that x and y are independent. So the fact that they are independent, if they are independent, I know that the density function of the pair will be the product of the density of each component. So here I use the independence of x and y. I obtain f x s z, f y s 1 minus z, multiplied by s. So here I have used the fact that x and y are independent. Now we are going to use the fact that I know the density of x and that I know the density of y. X follows a gamma A1, y follows a gamma B1, okay, and I remind you that the density of a gamma is given by this expression, okay? So for x, it's a gamma A1, alpha equal to A, lambda equal to 1. So I obtain what? Lambda equal to 1, so I don't have the first term. I have sz to the power A minus 1, exponential minus, so lambda is 1, so that is exponential minus sz. I don't have to forget the indicator function. Indicator function that sz is strictly positive, divided by gamma of A. Then I have what? For Fy, it's a gamma B1. Okay, so I use this one with lambda equal to 1 and B equal to, alpha equal to B, and I replace X by S times 1 minus Z. I obtain what? I obtain S1 minus Z to the power B minus 1. I have exponential minus S1 minus Z, indicator function S1 minus Z strictly positive, and I have to divide by gamma of B. And I don't have to forget, so to be clear here, this one is this one, this one is this one, and this one. Okay? So now here I have the joint density I am interested in. Seems to be not that easy to handle, but we are going to see that we can simplify a little bit the things. Okay? But if you write this, okay, you have the joint density of the pair SZ that is given by this expression here from the use of the proposition 16 in the course. Okay? So I can simplify a little the things. So now I can erase everything because I have used the proposition 16. Now I will just try to express this one in a little better way. So I continue here. So I have some simplifications to do because I have s to the power some 1, s to the power some 1. So I obtain s to the power, I have an s here, I don't have to forget, s to the power a plus b minus 1, because I have this term here, and this term here, okay? Then concerning the exponential with s, I have a single exponential with only s inside, that is exponential minus s here. Okay, that is this term, this one here, and then I have the term in z. So I have z to the power a minus 1, 1 minus z to the power b minus 1. I have no more exponential for sz because you have here exponential minus sz and here exponential plus sz, so you have simplification between these terms. Okay. So I have this one, and it remains what? It remains the gamma, that is over gamma of A, gamma of B, and I don't have to forget the indicator function. Indicator function that Sz is strictly positive, indicator function that S1 minus Z is strictly positive. Okay? Here I just compute, I say nothing, I simplify what I can simplify. Okay, that's it. Okay. For this one I have to work a little, because it's not that classical way. I want condition on S and condition on Z. Okay? And here I have condition on product. So, what can I say concerning this indicator function here? From the first, I know that the product SZ is strictly positive, implying that S and Z are not zero and have the same sign. So S and Z have the same sign, okay? Because the product is strictly positive. Here, the same for S and 1 minus Z. So at the end, I have S, Z, 1 minus Z that have the same sign, okay? It is the meaning of this indicator function. So S, Z, 1 minus Z have the same sign. So I have two possibilities. All strictly positive or all strictly negative. And we are going to see what happened in both cases. Okay, because I want to express this indicator function in a simpler way. That is having condition on S and condition on Z if possible. Okay. So if they are all strictly positive, I have my S that is strictly positive, I have my Z that is strictly positive, I have my 1 minus Z that is strictly positive. Why not? Okay. And here I will have my S that is strictly negative, my Z that is strictly negative, and my 1 minus Z that is also strictly negative. What can I say about this one? This one just means that S is strictly positive and that Z is between 0 and 1. For sure, it's something that I have already remarked from what I have done at the beginning. The set of the possible values for Z are to be between 0 and 1. Okay? Because it's x over x plus 1. What happened for the other situation? But I have S that is strictly negative, I have Z that is strictly negative, and I have Z that is strictly greater than 1. It's impossible. Because, okay, these two conditions are not compatible. It's not possible for being strictly negative and being strictly greater than 1. So at the end, I continue my computation here. I copy what I have done at the beginning. And I can write this product of indicator functions simply using this. It's the indicator function that S is strictly positive, indicator function that Z is between 0 and 1. And you have here a nice way to express the joint density. Okay? And I said that in fact, the exercise is now finished. A priori, no, because I have some question to answer. Okay, so I have the distribution of the pair, that is the answer to question A. And then they told me that I have to compute what is the density of S and the density of Z and see if they are independent. Okay? Are they independent? Yes, because in fact you see that here, and here you have expression depending on S. Here, and here you have expression depending on Z. It means that you can separate the variables. So they are independent. I can express the joint density as a part depending only on S and a part depending only on Z. They are independent. And now, a priori, I have to find the distribution of the components. So, a priori, I need to compute integral with respect to S and integral with respect to Z. It's not what we are going to do. It's not what we are going to do because, in fact, here I recognize someone. Not exactly, but not very far. So, what do you recognize? When I see this, okay, I see this. You have the beginning of a gamma distribution. Okay? You have the beginning of the gamma distribution for the first component, S. Okay? And I will show that it will be this one that I have to find. So what we are going to do is to make appear the density of a gamma, or gamma of parameter what? Gamma of parameter A plus B and 1. So what I do here, so instead of computing partial integrals here, instead of computing partial integrals, I recognize something that is not very far from one distribution I know. I make it appear, and it will be finished if I do this, because let's make appear the density of SA plus B minus 1, exponential minus S indicator function of S strictly positive. So it's the beginning of a gamma. If I want to obtain my gamma, I have to divide by gamma of A plus B. Now let's do it. Here I have the density of a gamma of parameter A plus B. But if I do this, it means that I have to multiply by gamma A plus B. Okay? And then I copy the remaining terms that are Z A minus 1, 1 minus Z B minus 1, indicator function of Z between 0 and 1 over gamma of A, gamma of B. And in fact, now it's finished if I do this. Why it's finished? Because suppose that you want to find the density of Z. You want to find the density of Z, so you have to compute the integral with respect to X, or to S, excuse me. But you know that the integral of this term is 1. So the density of Z is this one. And I know that they are independent. So the density of X will be the joint density divided by the density of Z. That is exactly this one. So at the end, I can say that the density of S is just a gamma of parameter A plus B and 1. But the result, we have proved at the beginning concerning the gamma distribution using moment generating function. But what I obtain also is that when I do the ratio x over x plus y, when x follow a gamma A1 and y a gamma B1, I obtain for x over x plus y this density function. And in textbooks, okay, this density function is called the beta distribution of parameter A and B. I don't consider it as a part of the program for the midterm exam. You don't have to know. Maybe you will have something about, but it's not something that I will consider from the course. Okay? So I want you to understand that it's finished if I do this. I don't have, in fact, to compute the integrals. And you will see that the homework is shaped in this way in order to make you fluent with this kind of computation. So the homework is in my web page, okay, and I will send you an invitation for a Zoom session on Wednesday or on Thursday. Okay? So good holidays also.